So please welcome with a very warm round of applause, Markus Brandt.
Thank you. Mic is working? Yeah. So, hello, welcome to my talk. Thank you for being here. So, this work has been done by many authors, Tianqian Dai, Amit Klein, Hai Schulman, and Michael Weidner. I'm the one standing here giving the talk. So, in case later I don't know an answer, I just blame it on one of the other names. So, first, who is this guy standing here? So, I work for the Technische Universität Darmstadt and the Fraunhofer SIT. Also, I'm a freelancer, and at the Technische Universität I also do teaching. So if you're feeling lectured in this talk, my apologies in advance. My special interests are number one priority, network security, then crypto and reverse engineering. So the outline of this talk would be, first I would talk a bit about public key infrastructures, then domain validation, what is it, how is it used. Then I would like to introduce the Offpath attack against these domain validations. And finally, defenses and some conclusions. So public key infrastructures. What are they? So let's start with a simple example. We have a client and we have a server. So in this case, our server is eBay. And we want to communicate with the server and we send our credit card information, for instance. We would not do this without encryption because obviously every attacker could eavesdrop and read our information, and we don't want to do that. So what we do to circumvent this, we use encryption. With encryption we have the key. Now we don't really know if we're talking to the right server. So we have a secure channel, but we don't know if the eBay server is on the other side. So to do this, we bind cryptographic keys to subjects. So in this case, domains. We call them certificates. And eBay, for instance, has a certificate that binds the cryptographic keys of eBay to that domain. So if some impersonator says, oh, I'm eBay, by the way, not the Comic Sans, it won't work because the root is self-signed or not signed by a certificate authority in your browser. To hand out these certificates, a mechanism called domain validation is used. Just as an info, you have around or more than 100 certificate authorities in your browser. If one of these authorities signs your certificate, your browser will say secure, or thanks to Google, it will say not secure. So there are different types of validation. Though on the right side you see there's organization validation and extended validation. This is done manually by people actually validating that stuff. It's very time consuming and of course expensive. And on the left side you see we have domain validation. This is automated, this is free or very cheap, and it's immediate. You sign up for it, you get validated, and you immediately get your certificate. So in this work we tested 17 CAs that perform domain validation. These 17 CAs represent over 95% of the whole certificate market. Little spoiler alert, 5 of them were vulnerable to our attack. And just as a small reminder, we only need 1 CA, so it doesn't matter if it were just 5. 1 would be enough because your browser will accept it and say it's secure. So how does domain validation work? We have a little flowchart here, and on the left side you see a user applying for a certificate, and on the right side you see the certificate authority. So a user would send a certificate signing request to the web server of the certificate authority. Then in this example we use mail validation. So we select, we want an email to the hostmaster address of this domain, and we will get a verification code to this domain, to this email address. So to do this, the DNS resolver of the certificate authority has to resolve the mail server. So it will, of course, ask the mail server of the user, what is the IP address for your mail server? The mail server will then hand out the IP address. The mail server will send the verification code, and then you can download the certificate by entering that validation code. So you see the resolving there takes a big part in this domain validation. So just as a short refresher, how does resolving domains work? So here we have a client, and if you want to access a domain, you have to know the IP address. So you would contact a local DNS resolver, and that would get the IP address from the name server. Usually this is done recursively, so it would ask for the name server for .com, then ebay.com, and then nsebay.com. Then the final name server we contact sends a response, and this is cached into the resolver. And then the resolver will answer to the client, okay, this is the IP address. So in case you're connecting, you're asking for the same domain again, and the DNS resolver has this value in its cache, it will reply from the cache. Actually, there are dark gray arrows you cannot see. So just let your imagination play. Then I would start the next part. Offpath attacks against domain validation. So for our attacks, we always try to assume the weakest attacker. The offpath, or spoofing attacker, as it's sometimes called, can only inject packets. So we can only spoof packets in the name of others. We cannot read packets, nor can we modify or delay packets in the flow. For this, we could try something like this. So we have a client and we want to resolve a domain name. We already discussed this. Now, the interesting part, we would expect a response from the name server, but if we as an attacker are faster and can craft this response, the DNS resolver will then cache the wrong value, our value, and will deliver that to the client. To circumvent this, because it's pretty obviously a very easy attack, there are some countermeasures. So one is you send from a random port. So initially this was done from a fixed port number. That was very easy to guess because it's a fixed port. And nowadays it should be randomized. So if you want to forge the response, you have to know the random port that has been chosen for the request. And every DNS query includes a transaction ID. This is just a random value to make it even harder to guess. So with these two values, you have 2 to the power of 32 values to guess, and that's in the time frame when the original name server will reply. So we did some calculations, and in average, this would take 2,000 seconds to guess. So even if your name server is on the other side of the world, it will be faster than you're guessing. So, just as a small insight, probably you all have seen an IP packet. So this is an IP packet. The next part of a DNS query would then be UDP, because DNS queries are based on UDP. So here you have the source port. This is the port that's randomized when you send your query. And inside that UDP packet, you have the DNS header. And you see the first field in the DNS header is the transaction ID. That's the other value you would have to guess. And finally, in the payload, you would have all the sections. So there are different sections: question, answer, authority, additional. And the challenges that we face are we have to modify communication without seeing it, because we're an off-path attacker. We want to overwrite the cache record with an incorrect record or with the record we choose. And we want to exploit this to circumvent PKI authentication. So our goals in 3 steps: create a correct response, inject into DNS cache, and issue a spoofed certificate. So let's start with number 1. And for this, I have a little example. So actually, that looks very funny. So in the middle, there's all the network with dark gray. So dark gray is kind of missing. And the clouds are connected. So on the left side, you have Alice. And Alice wants to send a packet to Bob. Bob, how much I love you. So if the network in the middle doesn't support packages that large, it would fragment the packages. These two fragments would then be sent to Bob, and Bob would just reassemble them and get the message. For these fragments to work, they have to use the same IP addresses, ports, and the IP identifier. So the IP identifier is basically used to group fragments. Of course, fragmentation can also be requested. So if you set, for instance, the don't fragment bit on a packet, you get a response like this. You send the packet, it's too big for the network. You get an ICMP message, too big. I'm sorry for the overhead. But I don't think we can fix that easily. Just believe me, it was there. So this ICMP fragmentation needed packet looks like this. So you have a normal IP header, which is sent from the host sending it. Then you have the ICMP header, which says packet was too big and includes some additional informations like the MTU. And then you just have a copy of a fraction of the packet that was dropped because it was too big. So forcing this fragmentation would be interesting for our attack. We could force our victim into fragmenting packets. So we did some testing, and among the Alexa 5,000 job sites that allowed the reduction of the MTU, 33.4% allowed MTU sizes a big larger than 269, and 11% allowed even lower than 296. These ICMP messages can be sent by anyone. Just as an example, there's an ICMP message, destination not reachable. This can obviously not be sent by the destination. So it's by design that everyone in the network can send these messages. And there's an interesting thing to note. OSs typically don't check these bits that have been sent from the first packet for UDP, because UDP is considered stateless. So if you respond to a UDP packet with an ICMP too big message, the OS doesn't check, did I actually send a packet? And was that packet actually larger than the value? So to use this, we could do the following. So you've seen this already before. We have our IP header, the UDP header, and we have like the beginning of the DNS header. And actually that would be a nice part to cut the packet. So if we only modify the second part, we can circumvent the randomized port, because that's in the first fragment. We only have to edit the second fragment, so we don't have to know the port. And we don't have to know the transaction ID. But now you might ask, what about the IP identifier? Isn't that supposed to be random? And just as a reminder, though, this is the RC from 1981. So the idea of the IP identifier was to set the identification field to a value that must be unique. You see, there's no mentioning of randomness in the original draft. Later on, people learned that it might be smart to randomize these. Some people are laughed at when they randomize these kinds of things and their performance gets a bit worse. A quick hint to OpenBSD. But actually they're doing it right. So how can we make these identifiers unique? So the most obviously would be we just use real random values. So very few servers in the internet we tested use random IP identifiers. And the reason for that is probably quite understandable. It's complicated. You need a lot of entropy. And of course, it's just overhead. So if you have like a big server running and you really have to ensure random IP identifiers for every packet, that's hard. So the next best thing you could do is you have a per destination IP identifier. So you kind of randomize them, and for every destination, you just use an incrementing IP identifier. So we checked less than 40% of the name servers we checked did this. This is currently the default in Linux. And there are also attacks that show how you can measure how many IP or how many increments have been sent to another destination. So this is in the footnote. I hope you can read this. Otherwise, I can include it later. And the third thing, how you could do something that would make these IP identifiers unique, is just you increment them. If you sequentially increment them, then you don't have duplicates. You don't have to check for these duplicates. That's also the thing you have to check for the real random identifiers. Because if you use real random values, you also have to check, did I use that value before? So just using hardware random number generators wouldn't be sufficient for this. And the sites we checked, over 60% of the Alexa top 10,000 domains use incremental IP identifiers. This is, of course, very easy to attack because you can simply guess by adding +1. And you can very easily estimate this. So you just contact, that's already a question. For this, it was the domains we checked.
Could you repeat the question? Could we just quickly repeat the question?
So the question was if it was just the domains or could you, or the DNS servers. So correct. But before we attack, we make a statistic about what the internet looks like. And because Alexa doesn't have many DNS servers, we used domain normal web servers for this. But we had some more precise numbers, which included the CAs involved, and I think you understand that we had to strip these slides because the CAs were not really fond of these slides. So that's why we have this simple version now. Another question that you might have is, what happens if the second fragment arrives before the first fragment? So there are different things that could happen. So usually, operating systems keep these packets and wait for the first fragment. So Windows keeps 100 of these fragments. Linux only keeps 64 of these fragments. In older Linux versions, it took way more. It was over thousands. And this value can be set via the syscontrol value ipfrag max dist. So now we know we can just modify the second fragment if we get this attack working. So our next step would be make it stick. So we want to inject it into the cache so we can use it later. And for this, I have another example. So you ask the DNS resolver for a domain name. And in this case, you see it already has some values in the cache. So there's a value for domain and for the name server for domain. And we ask for subdomain. What could happen now is the answer could be something like this. So we have no answer. And the authoritative server section says, OK, the name server responsible for this is NS domain, which is already in the cache. But in the additional section, it says, OK, the IP address of NS domain is 9999, which is different from the one in the cache. So now some resolvers think, oh, it has a new IP address. I should just update this value. And by doing this, we have overwritten the value in the cache. Of course, this was the most simple example I picked here. And not every name server is vulnerable to this. This looks interesting. So on the side, you see there was a study of DNS cache, DNS poisoning attacks. And we found 18 different payloads that worked amongst different name servers. Because if you have a name server, or if you're CA and you have a setup to do all this stuff, then you have different policies, which records to keep and which records to overwrite. So I hope this table works. Okay, only the gray is missing, the rest is readable. You see, different DNS servers are vulnerable to different payloads. So there are currently no name servers in this test that are not vulnerable to at least one. So we are still working on it to check for some new versions. But this is the current version we have. And you see some servers, so Google kind of did their homework. They have a big column of no's and only a few yeses on the bottom.
So that table is an example why you don't want to sit in the back but up in the front, because in the front you can at least guess at what's standing there.
Yeah, and the contrasts are a bit messed up, so that's not my fault. I don't want to blame anyone here, but actually I do. Okay. So if we want to try to attack our victims, we can fingerprint the DNS server. Once we find out which DNS server they're actually using, we just select a payload which is successful against these DNS servers, and then we can poison the DNS cache with that payload. And if we do that, we have an incorrect value, or from our point of view, correct value in the DNS cache we can use to issue the spoofed certificate. So now we can get to the final step and get our certificate. So now I have another flowchart, and now the attacker and the victims are a bit simpler, so we didn't include all the servers. So just imagine that the web server and stuff like this, name server, mail server, are all in that line. So the first thing you would do as an attacker would be you tell the victim that fragmentation is needed because you wanted to reduce the MTU so you can forge the second fragment. Then you estimate the IP identifier. This is pretty easy, especially if it's incremental. You just check the speed and then you can guess. And if you're using Linux, or if the victim is using Linux, you have 64 tries. So if you know it's around that value, you can just send some more and somehow you will find a match. Then you will send the second fragment of the query that's supposed to come from the victim's name server. And here, I hope this is readable. Yeah. So we just point the IP of the mail server to our address, which is 6666 in this example. And then we ask for certificate. So we log on to the website and we fill out everything. And once we click validate, the DNS server of the certificate authority will check for the IP address of the mail server. The DNS server from the victim will reply. It will send the first and the second fragment, but the cache will drop the second fragment because it was already there. So now we have the real first fragment combined with our forged second fragment. And now the mail server of the certificate authority will send that email with the verification code to our mail server. And once we have this verification code, we can just download the certificate from the CA's website. I'm just waiting for the photos to finish. And now we succeeded. Now our eBay is as trustfully, at least for the browser, as the real eBay. So what could you do against this? So there are some short-term defenses and some long-term defenses. So let's start with the short ones first. One would be disable caching. This makes the attack much harder because you can only do it like in real time, but not impossible because you've seen the way to cache the to poison the cache would be the same. You would just do it in real time when you get the real response. So this way was just more relaxed because you just poison it at the beginning and then you just use it. Then you could disable IP fragmentation, but this will disconnect some networks. So not every network supports every MTU. For instance, PPPoE still has a 1492. And what you also could do, force DNS over TCP, but there are also Offpath TCP injections attacks, and it offers no security against man-in-the-middle attackers. So we now just demonstrated it with the weakest attacker, which means that every attacker that is stronger than this weakest attacker can do this easily. So for a man-in-the-middle attacker, the attack you've seen before is very easy. So you could just make it harder for the Offpath, but the man-in-the-middle would still be able to do it. Long-term defenses, you could do DNS over HTTP and TLS, but that would be like securing the PKI with the PKI itself. So it already sounds weird, and I don't think it's a good idea. Then DNSSEC would, of course, be a solution if it was fully deployed. And we also presented something in a paper called Domain Validation Plus Plus. So this is supposed to be a drop-in replacement for the conventional domain validation. So the validation is performed from multiple vantage points. And this secures even against man-in-the-middle attackers because they cannot control all of the internet. So if they just control 1 or 2 passes, you will see that the responses don't match. And all of these vantage points have a local resolver, which of course have caching disabled. Otherwise, it would just be like a one after the next attack. And there are also some hardened configs you can use, like for Unbound, for instance. The main part that connects everything is called orchestrator, and this collects the answers from the vantage points. And the validation succeeds if a majority of these vantage points return the same value. And to communicate with these vantage points, HTTPS is used, but not with the PKI. You just have fixed certificates which you copy into a folder because, like I said, solving a PKI with a PKI is not a good idea. So we did some simulations doing this, and we assumed different attack success rates. And you can see if you have like a success rate of 25%, which is the lower line, and probably easier to read from the back. You see if you use 5 vantage points, it's very close to 0. And if you have like a very strong attacker that has a 75% chance to succeed, you see if you just use enough vantage points, it becomes very unlikely for them to succeed. So general advices would be disable caching for domain validation resolvers, because doing it for resolvers in the internet doesn't make sense, because then every request would have to be resolved recursively. Then, of course, adopt domain validation plus plus, and people should harden their DNS resolvers and limit fragmentation to reasonable values. So we've seen some of these networks allowed MTU sizes of 300 and below. That doesn't make sense. So we would suggest 1280 would be enough, because that's the minimal packet size for IPv6 anyway. And if you're not ready for IPv6, then you're not ready for the future anyway. And of course, deploy DNSSEC. But deploying DNSSEC is challenging. So we did some study on DNSSEC, and we found that 1/3 of the signed domains cannot be validated because they are just misconfigured or some other things went wrong. 35% of these domains used shared keys, which, if you know a bit about crypto, is in general not a good idea. 90% of these were signed with keys lower than 1024 bits. And 70% of these domains never refresh their keys. So they're using the key over and over and over, which generally is not a good idea. You should rotate the keys. Which would bring me to my final part, the conclusion. So the deployment of security internet is challenging. So this was just example. Things like this exist in other systems too. And as you've seen, this cache optimization was not like intentionally bad. They had good intentions to make things faster and perform better, but they forgot about the whole thing and the whole horizon. And that's the next point. You can make local enhancements to security work if you just understand the landscape, so you don't have to be fixed to one part. That's what corporates usually like to do. Put people into fixed positions and they only care about this one part. But you still should check the other part, because everything interacts with each other. And you should see behind that horizon. And you should provide security that can be partially adopted. So one example which is not partially adopted is DNSSEC, because if not everyone is using it, it's kind of useless. So if everyone would be using it, we would be much safer today. And the last point, we should give incentives to adapt new technologies prior to breaking them. So usually we break things, and because they're broken, then we fix them. Maybe we should update before that. Then I would like to thank you for your attention and gladly take any questions. And if you have more questions, this is the site for our tech with videos and live demonstrations. Well, recorded live demonstrations. So I cannot supply you a live demonstration. I guess you understand.
Thank you very much, Markus. If you want to read the URL, you have to come up front.
Hi, thank you for the presentation. Great stuff. I have a question about domain validation plus.
Yeah.
So, have you done any study about the overhead that it causes? And if so, do you think that overhead would be feasible in today's internet? If the autonomous systems would be able to adopt that approach?
The overhead is very feasible if you just think about how much traffic does a normal DNS lookup generate. And you just multiply this kind of by 10 and you add like a little HTTPS header. So you're still talking about less than 1 kilobyte. Correct, but it's so the orchestrator still has to do overhead, but it's not like you would validate 1,000 domains per second. So it's still something that can take time because validation is not that often requested.
And getting to my second part of the question, sorry about this. Do you think autonomous systems would be prone to adopt such a technology considering that overhead?
You mean certificates authorities, right? Yeah. Yeah. So we are in the talks with some certificate authorities, and they are very looking into this.
Yes. So for me, this is going to be more of a comment rather than a question, given that I asked you a lot of questions at CCS already.
Correct.
So what about the minimum buffer size that EDNS can specify, at which point which Let's Encrypt, for instance, deployed, which breaks the attack? Then there's a question that this doesn't work for IP version 6 because you have a minimum buffer size of 1,280 bytes. There's also the part that you're not mentioning, 8-hour defense, which was presented at NDSS around 9 months before your paper, as well as the deployment of Let's Encrypt on the multi-vantage point verification, which is basically the same thing you're doing, which was also presented at Usenix Security by a different group. There's also the part that Bind9 as well as Unbound have protections against fragmentation in there. Unbound has a commit from the 10th of April 2014, and Bind9 is protected since the 2nd of November since 2016. Both of those you're not mentioning. So I'm wondering why you're still not acknowledging that other stuff is there.
Okay, was that one question or?
No, there was more a comment and then a question at the end where you're not acknowledging that what other people have been doing.
So actually we acknowledged it in the paper, as you all saw.
No, this is not in the paper. The paper acknowledges a poster from essentially a few years ago, but you're neither citing our NDSS paper from this year as well as the Usenix security paper.
Yeah, you're talking about bamboozling paper. That paper was released after our deadline to CCS.
But not after the camera ready for it. And our paper was published before the actual submission deadline for CCS was.
Yeah, but that was a completely different approach in our view.
It was a
So
different approach,
not,
but it is
was something
entirely
completely
related
different.
and protects even more attacks than your defense protects against.
So basically, you have additional information you would like to point out. So if you're interested, So if someone is interested in that, hit him up, and he will give you more information. Otherwise, take it offline. Sorry. Any further questions? Yes, Hanno. Give me a second.
Yeah, I have a few questions. One would be, you say that in your DV++, you say that you use a majority of the points. Why not just all of them? Because like if any of them fails, it seems like something is strange.
So in the actual implementation, you can choose how many. So the default is just majority. If you want to be more secure, you can also say all of them has to reply with the same response.
And then like I'm not super familiar with the UDP IP details, but it feels to me that using TCP DNS would kind of, I haven't really understood. You said there are other attacks, but you didn't really expand on that. It would feel to me that this would kind of at least kill most of the scenarios here.
So of course, TCP would make it much harder, but it doesn't make it secure by default because still you are vulnerable to man in the middle.
Okay, that is, I mean, kind of by design. We cannot fix this in the current model of domain validation, but it would kind of beat all these poisoning and off-cache attacks, right? Off-path attacks.
Probably.
Yeah, and the other would be this IP ID randomization. So your argument was that like this is too slow to be deployed, and that's why Linux doesn't do it.
I can only guess why people don't do it, but
Because
real
it feels to me
randomness is.
like if your randomness is too slow, then you should work on your random number generator and not
If you ever
avoid
worked
using it.
with real secure randomness, you know how slow it is to gather. So, for instance, there is the dev random device in Linux. Which
Yeah, but
is
that's like stupid. I mean,
Yeah.
you use a non-blocking random number generator, and then you can have really fast random numbers. That should not be an issue. I
yeah, but
think.
how many packets do you generate per second on a big site? And you also have to check, was that IP identifier not used before? So it's a
how
big
long is it?
overhead.
Depends on how long it is. But okay, yeah.
Further questions? What? Silence? Nah, come on. No? Well, in that case, let's say thank you very much, Markus Brandt. Thank you.